Can you guys hear me? All right, let's get started then. Okay. So we're gonna start with the um, light behavior as a wave. Okay. So the first question, you guys, I want you to try. Okay. Let's get started here. What is the frequency of a red? What's the frequency of the red light if the wavelength of the red light is 656.3 nanometers? What did he say? Sorry. 640, okay, 656.3 nanometers. Done? Zoe? Okay. So when a light behaves in the form of a wave, um, this is a part of the electromagnetic radiation. Frequency is equal to C or lambda. Frequency is speed of light divided by wavelength of the light. So frequency of the light is 3 times 10 raised to 8 meters per second divided by 656.3 nanometers. Nano is 10 raised to negative 9 meters because the meters and meters cancels. What do you guys get here? Okay. Zoe, what do you got? Mm-hmm. The unit is per cycle or hertz? May- You guys cool with that? Okay. Do you want one more or should we move on? Okay. Try this one. What is the wavelength? What is the wavelength of a light, what is the wavelength of a light? If the frequency, if the frequency is 107.1 megahertz, okay. So lambda is equal to c over frequency. It's 3 times 10 raised to 8 meters per second. Frequency I've given was 107.1 megahertz. Mega is 10 raised to 6 hertz or per second. Same thing. Just tell me what you guys got. Well, okay, next one. Next is Planck's equation. Okay. Planck's equation. Planck's equation is E is equal to h nu, that's h times frequency, or E is equal to hc or lambda. So according to Planck, the light behaves like a particle. So instead of going as a continuous wave, it now is an individual package called photon or quantum. So we are calculating for each, this E stands for each energy of the quantum or photon. Okay, so this is your photon or quantum. Got it? So find the energy of the red light. Find the energy of the red light, which is with a wavelength of 656.3 nanometers. Six 56.3 nanometers. You have to find the energy of the red light. What is the units? What is the unit of your answer? Hmm? That's what I'm saying. One of the things I see as a weakness in you guys is you don't focus on the units. Without units, see, an answer doesn't mean anything, right? So I told you this is the energy of one quantum. So this is joules per quantum or joules per photon. So it's the energy of one photon. So this is the Planck's constant. Speed of light, of course, we know is 3 to 10 raised to 8 meters per second. And wavelength is 656.3, 10 raised to 99 meters. Tell me, what do you guys get? What do you got? Where did you get that one? Make sense? So, as this is behaving like a particle, like this. So we did find about one photonic energy. That's why the unit says joules per photon. I would like you to convert this joules per photon to kilojoules per mole of photon. Try that. Current to kilojoules per mole. That's why the word mole comes into picture, because now it's acting as a particle. So when they ask for kilojoules per mole, so you have to get a joules per photon, then go to this point. Make sense? Okay. Alright. Did you guys study photoelectric effect? photoelectric effect. Photoelectric effect. Okay. Hmm. Okay. I need to teach you guys this. This is important. Now, according to classical physics, light was in the form of a continuous wave. Okay. Then Max Planck did the black body radiation experiment. So where he took a black coil. Have you heard of the black coil experiment? Okay. I don't know. Can you guys hear me now? Okay. Uh, okay, I don't know. Okay, we'll try. So Max Planck did an experiment called the black body radiation. Have you heard that? Okay. So what he did was, this is Max Planck. So this is electric stove at home basically. So you have a knob, and he increased the knob all the way to high. As he turned the knob on, what he was finding out was the color of the black body went from light orange to dark orange to red. And then, of course, in the electric stove, there is a limit how much heat you can give. But in his experiment, he just kept increasing the heat all the way. What he was expecting was, as the intensity of the heat increased, the intensity of the color that was given out by the electric stove should also be darker and darker and darker, like dark red, 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 and so forth. That because in the classical physics, energy, light was in the form of a continuous energy. Just it kept increasing, increasing, and increasing. But what he found out was, after a certain amount of heat, the intensity of light, instead of going like this, just came like this. So at that time, he thought, if the light were to be continuous, this is what I should have been expecting, the intensity of the light. But I didn't get that. I actually got to a point and then it just fell. Then he thought the light given out is not continuous, but in the form of packets called quantum or photons. The name photon was given by Einstein by conducting the photoelectric effect. So what is a photoelectric effect? So what he did was, he took a glass container, no, nothing in it. Then he took 2 electrodes. On this electrode, he had a metal surface, a metal piece. And this was, of course, connected to the voltage. This was positively charged, this was negatively charged. So initially, this surface was called active metal surface, or active surface. So initially what he did was, he used light of high wavelength. As you know, the equation E is equal to hc over lambda. As the wavelength increases, the energy decreases. So he used a very low energy light on that active metal surface. And of course, as expected, nothing happened because that energy was so minimum. Then he decreased the wavelength. As you decrease the wavelength, frequency get increased. As the frequency increases, energy increases. So he used a much higher frequency wave. As soon as he put the high frequency light onto that active metal surface, as you know that metals are made up of metal atoms and atoms contains electrons. This energy light was able to knock out electrons from the active metal, and it was positively charged. Electrons are negative. It started attracting, and the current started to flow through the system. This is called the photoelectric effect. So lots of things to discuss in this. How did he support the concept of quantum light instead of a classical light? How did he support Einstein? This is what he did. If light were to be continuous, doesn't matter what the wavelength was, it would keep impinging on this one, and eventually it would remove the electron. But he found out that certain wavelengths of light, which is high wavelength light, could not remove the electrons because the light was not continuous. If it was continuous, it could have removed it. Now it is coming out as packets of energy. If each packet of energy could not have the energy to remove an electron, it doesn't matter how many of them are hitting the same spot. So the best logic to understand this is, if I take a ping pong ball and throw it at glass, it's not going to break the glass. If I take 10,000 ping pong balls, if I throw it, it won't break the glass. But if you take one steel ball and if I throw it to the window, glass window, it's going to break it, because that steel ball have enough energy to break the glass window. Same here. So the wavelength of the light or the frequency of the light will decide whether an electron can be removed from a metal surface. The minimum energy required to break the electrons from the metal surface is called threshold frequency. Very famous called threshold frequency. That's the minimum frequency of the light required to remove an electron from an active metal surface and have the current flowing. That's why it's called photoelectric. It produces current effect. Until today, we see this. When you go for when you're driving on the road and you see the construction signals, you see those solar panels. Have you guys seen the solar panels? Okay, how does the solar panels work? So I don't know if you observed it, it usually is at an angle, usually 45 degrees. So the sun rays are falling on it, and sun rays have enough energy to remove the electron from this active metal surface, and the current flows. So it is one of the most important applications is the photoelectric effect. So there are two things happening. It has to have a certain energy, and it should remove the electron and make sure it moves towards the positive electron. So the energy of the light, or the energy of the photon, must be greater than or equal to the kinetic energy of the electron going towards the positive electrode plus the binding energy of the electron to the metal. So what it means is, I need to provide first energy to break the bond between the electron and the metal surface, and then speed it towards the positive energy. This is called work function, W. So this is the equation they use to decide which light we should use for a certain active metal surface so that the electrons are moving towards the positive charge, positive electrode before the current flowing. Does that make sense? So remember, first it is basically the electron is held to the atom, right? So the light should come, break that relation between the atom and the electron. Then it should have some speed to reach the other side, right? Just removing doesn't mean that it's reaching the other side. And you can expect the binding energy should be low because electrons have hardly any energy required. So these are very small values, but that value is required so that you know which light to use. Every metal surface has a unique threshold frequency that will break the electrons. Joey? Does that make sense? So have you heard, so you have not heard about photoelectric effect then? These things? Okay. But does it make sense now? Okay. All right. I'm sending a picture. Did you guys receive it? Sorry, I didn't hear you. So basically, what they're saying is light that is coming out is not continuous. It's not like a ramp. It's like a step. Okay. So they are saying the work function of titanium metal is so many joules. Calculate the kinetic energy of the ejected electrons if the light of frequency that's falling on it on the active metal surface is so much. That means what they are saying is that the energy they are putting in is enough to move the electrons towards the positive electrode. Okay, tell me the answer. Yeah. Zoe, what do you got? Huh? Okay. Let's try. Whether we make sure it's in the scientific notation, okay? So proper scientific notation. So HV light kinetic energy of the electron plus the work function. So the question they're asking is what is the calculate the kinetic energy? Okay. So kinetic energy is equal to or greater than frequency of the light 2.5 into 10 raised to 15 minus 6.93 10 raised to negative 19 joules. Joules, so this should be joules. So the kinetic energy will be less than or equal to, because it cannot be more than that, it has to be maximum. 6.626. Alright, I'm getting 9.64 times 10 raised to negative 19 joules is the kinetic energy of the electron. Yeah, yeah, yeah. Zoe? You got this back? Can you double check that quick, please? Can you double check? Wonder why it happened? That's order of operations will be taken care of by the calculators. Okay. All right. Okay. Sending another problem. Got it? Done? Okay. A clean metal surface is irradiated with light of three different wavelengths. The kinetic energies of the electron are 2.9 10 to the negative 20, approximately 0, that means very, very small, and 4.2 into 10 to the negative 19 joules. Which light has the shortest wavelength and which has the longest wavelengths? Okay. All right. So look at this equation here. Right here. Okay. All of them, we are dealing with the same work function. So let's take this out for a second. Okay. So kinetic energy of the electron is less than or equal to hc or lambda light, because we are looking at the wavelength. So there is an inverse relationship here. As the wavelength of the light increases, the kinetic energy of the electron decreases. So the question they're asking here is, the kinetic energies of the ejected electrons are so lambda 1 is 2.9 into 10 to the negative 20. Yeah, because the work function is the same for all three lights, because it's the same metal. So it won't make any difference. Yeah. So the kinetic energies of the electrons is 10 to the negative 20. So remember, the one which has the highest wavelength will have the lowest kinetic energy. So the lambda 2 should have the highest wavelength, because its energy is almost equal to 0. Are you with me? So that's, and the lowest would be, so not highest, let's call this longest wavelength. Longest wavelength. And the one which has the highest energy should have the lowest wavelength. So 4.2 into 10 to the negative 19 joules. So that's lambda 3. Shortest. Because its energy is the highest. Does that make sense? Are you sure? Okay. But does this make sense to you guys? This is more important. I actually wanted you to learn that the work function does not change because the metal is the same. If the metal changes, of course the W changes. So the relation here is, as the frequency increases, kinetic energy of the electron increases. Or if the wavelength of the light increases, frequency decreases, kinetic energy decreases. So there is so more stronger the light is, more faster the electrons will travel. Okay. Should we try one more or should we move on? Okay. All right. Okay. So we have an active metal surface and 3 different wavelength lights are falling on it. Which one will have the lowest kinetic energy of the electron? Lowest kinetic energy. Tell me the answer. Yep. Did you have the same answer? Okay, cool. Now makes sense, right? So you know the fundamentals. So the what I would do is when you have anything about the wavelengths, I would convert these to frequencies. So this is the highest frequency, that's our highest wavelength. So this is the lowest frequency. This is the minimum. If this is the minimum, the kinetic energy would be minimum of this. Make sense? Okay. As we're left with a few more minutes, so you guys know electronic configurations? I wanna take it up some easy stuff today, right now. Okay, write down sulfur electronic configuration, the shorthand and the longhand. Zoe? 1s2, 2s2, 2p6, 3s2, 3p4. Right? Trichromium. Yeah, answer. No. Yeah. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. The Hund's rule. 3d5. Remember the 4s2, 3d4 can be made into 4s1, 3d5 because of the stability criteria. The Hund's rule. Remember when they're so close? Do you remember that? Try copper. Somebody answer that. For S1 3D10, you have to have 30 electrons, right? Copper is what? No, 29. Copper is 29, so you have to have 29 electrons. Because otherwise it would be 28. Zoe, did you get that? Remember, that's why I asked you guys, copper and chromium are the exceptions to the rule. And you guys specifically need to remember that. Chromium, that's what the two examples I just asked. You guys good? Do you remember which noble gas you have to use to shorthand? So it has to be immediately preceding the element. Valeria, you with me? So which noble gas would you use for boron? Hey, for boron? Yeah, which noble gas would you use? Zoe? For boron, which noble gas you have to use? Helium. That's the one that's behind boron, right? Valeria? So you have to use the one that's immediately preceding the element. Got it? Okay. Alright guys, see you later. You guys have to keep working. And I'll be sending some list of books you guys need to buy because we have to start with the AP Chem preparation now. Okay? Merry Christmas guys. Bye-bye.